This is a second lesson on radioactive decay. It's really important that you've watched the first lesson on simulating radioactive decay using dice in order to really access this lesson. So by the end of this lesson, you'll be able to state how we know that radioactive elements decay exponentially. You'll be able to use the equation A equals lambda n with confidence and be able to calculate lambda, the decay constant, using the half-life. You'll be able to derive the equation for half-life, which is t to the half is log 2 over lambda. You'll be able to explain the meaning of the gradient and the intercept of a graph of the log of the parent nuclei against t, using the equation n equals n naught e to the minus lambda t. You'll be able to calculate the number of parent nuclei in a sample, knowing the mass and the molar mass. You'll be able to apply the decay equation to examine questions of confidence, understanding the need to match the units of lambda and t. So let's start by looking at the key concepts of radioactive decay. So if we plot the number of parent nuclei against time, we know that it decays exponentially and that it has a half-life, and every half-life the number of parent nuclei drops by a factor of 2. We can also plot activity against time and we get exactly the same relationship, because activity is directly proportional to the number of parent nuclei. We can prove this by plotting a graph of the activity against the number of parent nuclei. We get a directly proportional relationship where the gradient is the decay constant, which depends on the probability of the nuclei decaying. So we have activity is directly proportional to the number of parent nuclei, A equals minus lambda n. The minus sign tells you it's a decay, not a growth, but we don't use the negative in any calculation. So there are two reasons why we know this is exponential decay. First of all, the value, n or a, drops by the same factor in equal time intervals, which is t to the half. Secondly, the rate of change of n, which is the activity, delta n over delta t, is directly proportional to n itself. So how do we write this exponential decay mathematically? So we have the number of parent nuclei left after a certain time n is equal to n naught e to the minus lambda t, where lambda is the decay constant, and this depends on the probability of decay, which is governed by the half-life of the source. N naught is the initial number of parent nuclei. We can also write A equals A naught e to the minus lambda t, as A is directly proportional to n. So now let's have a look at the relationship between half-life and decay constant. Well, half-life is defined as the time for the number of parent nuclei or the activity to drop by half. So if we use the above equation and we divide by n naught, we get a ratio n over n naught is equal to e to the minus lambda t, and when t is t to the half, that ratio of n over n naught is equal to 0. If we invert both sides of the equation, we get rid of the negative power, and so we get n naught over n is equal to e to the lambda t to the half, which is equal to 2. Taking logs to the base e, we get the log of e to lambda t equals a log of 2. So that gives us simplified lambda t is equal to log 2, leaving us with the equation for t to the half is equal to log 2 over lambda. It's important to remember if t to the half is in seconds, lambda is seconds to the minus 1. It's vital that lambda must be in seconds to the minus 1 if you're using the equation activity is a decay constant times the number of parent nuclei. And when using either of these equations, you must ensure that the units of time and decay constant match. For instance, if your time is in years, your decay constant must be in years to the minus 1. If your time's in hours, decay constant must be in hours to the minus 1. So let's now have a look at plotting logs to the base e and how we can use the graph to prove a logarithmic equation. Taking logs like exponential equation, we get the log of n is equal to the log of n naught plus the log of e to the minus lambda t. Remember, we can split the logs if they're multiplied together. Simplifying and rearranging in the form y equals mx plus c, we get the log of n equals minus lambda t plus the log of n naught. So plotting a graph of log n on the y-axis against t on the x-axis gives us a linear relationship with a negative gradient, where the intercept of the y-axis is the log of the initial number of parent nuclei and the gradient is minus the decay constant. Remember, we get exactly the same relationship plotting the log of the activity against time, as of course activity is directly proportional to n. Finally, the last thing we need to do is to look at using Avogadro's constant to work out the number of nuclei in a sample. So 1 mole of a substance contains 6.02 times 10 to the 23 atoms or nuclei, and that is Avogadro's constant. Secondly, the molar mass mR is the mass of 1 mole, which is in grams, and is the same as the relative atomic mass, which you get in your question. So the number of moles n in a sample will be the mass of the sample divided by the molar mass, which is capital M over mR, which is equal to n. Finally, the number of atoms or nuclei in a sample, given the symbol capital N, is equal to the number of moles times the number of nuclei in each mole, which is Avogadro's constant. So let's now apply what we've learned to example questions, which I've made sure cover all the techniques that you will need to use in exam questions. So our first question, we have a sample of iodine 131 with a half-life of 8 days, and it has an activity of 7.4 times 10 to the 7 becquerels. What will be the activity of the sample after 8 weeks? Well, the first thing we need to do is to work out the decay constant. So lambda is log 2 over t to the half, and we can keep t to the half as days, as we're not using activity equals lambda n. This gives us lambda in days to the minus 1. So to work out activity, we use the equation A equals A naught e to the minus lambda t. Putting the values in and making sure that we use days for time, so that's going to be 56, 8 times 7. Gives us a value of 5.8 times 10 to the 5 becquerels for the activity. So question 2 says a strontium 90 source has a mass of 30 micrograms and its half-life is 20 years. Remember, 90 will be the molar mass of strontium in grams. So the equation we need to use is activity A is lambda n. Now of course we don't know lambda or n, but we can work them out. So the number of strontium nuclei will equal the number of moles of strontium times by the number of nuclei in each mole, which is Avogadro's constant. To work out the number of moles of strontium, we can do the mass of strontium divided by the molar mass, which is 90. So substituting for n equals m over mr into the other equation, we get the following. It's 30 micrograms, which is 30 times 10 to the minus 6, divided by the molar mass, which is 90 grams, times by Avogadro's constant, which gives us 2.00 times 10 to the 17 nuclei. So we now have to work out a decay constant, which is log 2 over t to the half. Remember, t to the half must be in seconds, so we've got to convert 20 years into seconds. And this gives 1.10 times 10 to the minus 9 seconds to the minus 1. Finally, we can substitute the values now for lambda and n into the equation to get the activity in becquerels. So part B asks us to calculate the activity of the source after a time of 75 days. So we can just use the equation A equals A naught e to the minus lambda t. Remembering we must match the units of time and the decay constant. Our decay constant is in seconds to the minus 1, so we need to convert 75 days into seconds. This gives us the following activity. So the last part of the question asks us to give the time it would take for the activity to drop to 20% of its initial value. This is a ratio, and we're also asked to give our value in years. So the technique with percentages or fractions left is to divide through by A0, so you get a ratio A over A0 is equal to e to the minus lambda t. And in this case that is 20%, which is 0.2. So e to the minus lambda t is equal to 0.2. Therefore, if we take logs to the base e, we get minus lambda t is equal to the log of 0.2. So t is equal to log of 0.2 divided by lambda. And this gives us a time of 1.46 times 10 to the 9 seconds, which we must convert into years, which gives 46.3 years. So our final question is on using a protactinium source in a lab to find the half-life. The activity of the source of protactinium was measured every minute for 6 minutes, and the student plotted a graph of the log of A against T. So the first question is to explain how the graph can be used to measure the half-life of protactinium. So we have to prove this by taking logs of the equation A equals A0 e to the minus lambda t and rearranging in the form y equals mx plus c. The log of A equals the log of A0 plus the log of e to the minus lambda t. Notice I've kept this step to make it really clear to the examiners what I'm doing. So this gives the log of A equals the log of A0 minus lambda t. Rearranging it in the form y equals mx plus c gives the log of A equals minus lambda t plus the log of A0. Notice I've made it really clear to the examiner what's y, what's m, what's x and c, and I've also sketched a graph of what it will look like. So the next part of the question is to use the graph to calculate the half-life of protactinium, and we're asked to include an uncertainty in our value. So drawing the best fit line, I'm going to ignore one of the points and label that as anomalous. I'm also going to draw the worst fit line, which will help me to assess the uncertainty. This is very subjective, and you won't be marked down for your worst fit line. You'll be accredited marks for just showing the process. So the decay constant equals minus the gradient, and it must be in seconds to minus 1, which is equal to 3.85 divided by 6.2 times 60 to convert minutes into seconds. This gives us a decay constant of 0.0103 seconds to the minus 1. We can also do exactly the same with the worst fit line. Now we've worked out the decay constant, we can work out the half-life, which is log 2 over lambda. So this gives a value of 67 seconds for t to the half with the worst value of 75 seconds. We must also work out the percentage uncertainty. Remember, that's the magnitude of the worst value minus the best value divided by the best value times 100, and those are what those straight brackets mean. This gives a percentage uncertainty of plus or minus 12%. So the last part of this question asks us to calculate the initial number of protactinium nuclei in the sample. To do this, we need to use the equation A equals lambda n. So we first need to find A0. Well, we know the intercept of the y-axis, the log of A0, is 6.8. So inversing your log on your calculator, we get A0 is equal to e to the power of 6.8, which is equal to 899 becquerels. Using A equals lambda n, we get n is A over lambda, which is 899 divided by 0.0103, which is equal to 8.7 times 10 to the 4 nuclei. Finally, let's just review the learning objectives. So, you should now be able to state why radioactive elements decay exponentially. You should be able to use A equals lambda t with confidence and be able to calculate lambda using t to the half. you should be able to derive the equation for the half-life. You should be able to explain why you can plot a graph of n lambda over t and what the gradient and the intercept mean and why. You should be able to calculate the number of parent nuclei knowing molar mass and the mass of the sample. You should also be able to apply a decay equation with confidence and understand that the units of lambda and t must match.